Okay, so in this video, we are going to talk about topic 1.7, which is periodic trends. And the purpose of this topic is to explain the relationship between trends and atomic properties of elements and electronic stability and periodicity. So the first thing we need to talk about are the atomic properties. So there are four atomic properties that we are going to focus on. The first is ionization energy, which is the amount of energy needed to remove an electron. The second is atomic and ionic radii, which is the distance between two nuclei in a compound. We would sometimes think about this as the distance from the nucleus to the outside electrons, but which it kind of is, but it's really looking at the distance between the nuclei in a compound. Electron affinity, which is the energy change associated with adding an electron to an atom. So it's kind of the opposite of ionization energy. And electronegativity, which is the tendency of an atom in a molecule to attract shared electrons to itself. So the pull of the nucleus on the shared electrons in a bond. Okay, we're going to talk about ionization energy first. All of these atomic properties we are going to be looking at through the lens of Coulomb's law. So you need to think back to what Coulomb's law means, because we're going to be talking about two factors, because there are two things that play into Coulomb's law, which is the magnitude of the charge and the distance between the charges. Okay, so ionization energy, we talk about first, second, third, fourth, so on and so forth, ionization energies, which is referred to, which corresponds to the number of electrons that are removed from the atom. So the first electron that gets removed corresponds to the first ionization energy. The second electron that you remove is the second ionization energy, so on and so forth. So Coulomb's law applies to ionization energy because it depends on the attraction between the electrons outside in the energy levels and the protons in the nucleus. Okay, so there are two factors to this. The nucleus has positive protons and the electrons are negatively charged. So if you have a greater positive charge in your nucleus, it's going to hold on tighter to those electrons. If you have a lower positive charge in your nucleus, it's going to hold on less tightly. And the distance between the electrons and protons also plays a factor. The farther away it is, the less pull the nucleus is going to have. The closer it is, the more pull the nucleus is going to have. This pull of the nucleus on the electrons is the effective nuclear charge. Okay, so it's a measure of that effect that the nucleus is going to have on those electrons. You can also talk about, when we talk about ionization energy, it involves the concept of shielding. So when we're looking at ionization energy, we're almost always looking at the valence electrons, so the ones all the way out on the outside. When we start to remove electrons, you might drop down in an energy level, but we're always removing from the outside, so technically they're always the valence electrons. The farther out those valence electrons are, the higher the energy level, the more energy levels of electrons are between the outer and the nucleus in the inside. Those inside electrons can shield the nucleus or shield the electrons from the nucleus. So they act kind of as a barrier between the positive pull of the nucleus and the electrons on the outside. So the more shielding that there exists, the less that nucleus can pull. So that's that bullet point where it says the farther from the nucleus, the lower the effective nuclear charge, the less energy needed, because there's that shielding there in the middle. Greater distance also means less attractive force. More protons, but not farther away, means a higher effective nuclear charge. Okay, so as you move across the periodic table, so as we go across a row, you're adding protons because your atomic number is going up. So as you move from left to right across the row of a periodic table, you're adding a proton each time. But remember, the rows correspond to the energy levels, so your electrons are still going into the same energy level. Okay, so they're the same distance, but there's more of a positive charge. Okay, so you're not changing any shielding here between your nucleus and your electrons. So that means you have a greater charge, therefore it's going to hold on more tightly and you need more energy to pull those away. So trends, as you move from left to right, your ionization energy goes up because that your nucleus is holding on more tightly. You've got a greater effective nuclear charge. Therefore, it's going to take more energy to remove an electron. As you move down a column, as you move from the top to the bottom, you're gaining protons, obviously, as you move down the periodic table, but each row you're adding an energy level. So you're increasing the shielding of those electrons on the inside. Therefore, you're decreasing the effective nuclear charge, and you need less energy to be able to remove those electrons. Okay, next one, atomic and ionic radii. So distance between nuclei. Again, Coulomb's law depends on the attractions between the electrons and the protons, depends on distance and shielding. So same idea as before. Remember, these are all coming back to Coulomb's law. So the farther from the nucleus, which means the larger the atom, the lower the effective nuclear charge, so the greater the radii. More protons, but not farther away, the higher the effective nuclear charge, the more that nucleus is going to pull on those electrons. As they pull, they're going to pull them in closer, so you get a smaller atom. Trend-wise, what does this mean? As you move from left to right across a row, you're increasing the effective nuclear charge because you're gaining protons, but your electrons are going into the same energy level. So your atom is actually getting smaller. So even though you're adding protons and you're adding electrons, you're increasing the effective nuclear charge of the nucleus, but your electrons aren't going any farther away. So your more positive is going to pull on tighter to your negatives and pull them in and make them closer. The farther you get from the nucleus, so as you go down a column on the periodic table, you're adding energy levels, okay? So that since you're adding energy levels, those outside electrons are getting farther and farther away from the nucleus. You have a lower effective nuclear charge, therefore you have a larger atom. Okay, next, electron affinity. So electron affinity is kind of weird because it's referring to the energy released when you add an electron. So you get negative energy values. So the more negative a value, the more energy gets released. So in terms of Coulomb's law, again, the attraction between the electrons and the protons, distance and shielding. The farther the electrons are from the nucleus, the lower the effective nuclear charge. So as you go down a column, so the farther they get from the electrons get from your nucleus, it's getting bigger, the electrons are getting farther away. You have a lower nuclear charge. That means you're going to release less energy. So you're going to have a lower electron affinity. And then as you move across a row, you're gaining protons, but they're not going farther away. So you have a greater effective nuclear charge, so more energy is going to be released. So it's a greater electron affinity. And then lastly, we have electronegativity. So electronegativity is kind of funny because they're made up values. They range from 0.7 to 4. And electronegativity is, again, looking at the attraction. So just like everything else with Coulomb's law, deals with the attraction between the electrons and the protons, depends on distance, depends on shielding. So the farther away you get from the nucleus, the lower the charge, the less the attractions for the electrons. So as you go down a column, you're adding energy levels, you're increasing the shielding, decreasing the effective nuclear charge. Your nucleus is going to have less of a pull on the electrons, both in its own atom and the electrons in a bond. Remember that outside the valence electrons are the ones that are involved in the bonding, so they're still in the same spot. So the farther away from the nucleus those bonding electrons are, the less attraction the nucleus is going to have. So your electronegativity is going to go down. As you move across a row, the more you're going to gain protons, but your electrons are going into the same energy level, so they're not moving farther away. So you're increasing the positive charge, but they're the same distance, so they're going to pull them in, so they have a greater attraction for the electrons in the bond. So all the way down in the lower left corner of your periodic table has the lowest electronegativity. All the way up, not quite in the top right-hand corner, are your elements with your highest electronegativity. Fluorine is actually the highest. Noble gases do not have electronegativity values. Why? Because they don't bond, with the exception of some of the biggest ones. Okay, so you have to keep in mind that electronegativity is the attraction for the electrons in a bond. So it only occurs when they're actually bonding. So those are our 4 atomic properties and the trends that exist based on their locations on the periodic table.